everyone. This is Ron Sparkman for Mars Society's Red Planet Radio. I love Mars and opportunity you. And today we are speaking with Dr. Chris McKay from NASA Ames Research Center. Dr. McKay has a PhD in geophysics from the University of Colorado and works as an astrobiologist. He is also an authority on terraforming and Mars. You've probably seen him on one of a dozen hit TV shows he's been on, such as The Universe and How the Universe Works. Dr. McKay, welcome.
Thank you. Good to talk to you.
We're glad to have you. So let's start with a little bit more of an in-depth introduction. Can you tell us a bit about who you are and what you do?
Well, my main activity is planetary exploration. Mars is a particular interest because of the search for life there and also prospect for future human exploration, both of which are of interest to me and have been for many years. And I'm also interested in the search for life in the outer solar system, Europa and Enceladus. And I'm also involved in exploration and expeditions to extreme environments on Earth, Mars-like environments, like the Arctic and the Antarctic and the Atacama Desert, etc. So Mars, and more Mars.
Well, that sounds great. And it's really a lot where a lot of the research is going on these days is in these more extreme areas. And since we have yet to find alien life, what are some of the more practical aspects of astrobiology? And how are we going to see these grow in the future in your field?
Well, it's a good question. I think there's several areas that are sparking interest in this field. One is field work in extreme environments. As we go to different places on Earth, we learn more and more about life at the edges of survival under Mars-like conditions. And that's a very deep well that we can continue to draw from. I think there's also more interest in Mars as results from the missions come in, showing evidence of early conditions and defining the challenge of accessing the remains of life from early Mars and the search for still remnants of life today. I think it's clear that we need to drill deep on Mars to get to evidence of early life. Also, indirectly motivating the search for life on Mars is evidence of oceans in the outer solar system. The Europa and Enceladus results are shining spotlights on the search for life out there, and by reflection, that is been interesting and useful for the Mars folks as well. So I think there'll be growing interest in the search for life on Mars, partly in a sense is competition, if you will, with the Europa and Enceladus activities.
That's fantastic. And what is it about Mars that really has sparked interest in your field? What is it that says life could have been here? We need to go here and do a little bit more exploration.
The fundamental reason Mars is of interest is the evidence that at one time it had an Earth-like environment. And so we don't really know how life got started on Earth, but we see life on Earth, we see it all over the Earth, and seeing that Mars had a period in its history when it was so Earth-like is very compelling from the point of view of biology, because it says that however life started on Earth, whatever environment it took on Earth, that environment would have existed on Mars as well because of this basic similarity. And that basic similarity in path between Earth and Mars is also what makes possible, I think, the idea of terraforming Mars and creating a global Earth-like environment again. Mm-hmm. Mars once had an Earth-like environment. It could have it in the future. Now, this is in contrast, for example, with Europa or Enceladus. These are interesting worlds. They have oceans, but they're not at all similar to the Earth. They're not Earth-like in any sense. They may be still interesting biologically, but they don't have all the rich history and potential history or future history that Mars has, because it was Earth-like and we think could be Earth-like again. So Mars is in a special category, and it's the basis for thinking that is the evidence that Mars had widespread water on its surface billions of years ago. That's the core observation, and it's been repeated from mission after mission since Mariner 9.
And that's really one of the more interesting ideas with Mars past, is that it had the possibility to hold life of what we know so far, and it is possible that is actually where life came from via panspermia. We've talked about the ideas of extremophiles such as the tardigrade and the possibility that life came from elsewhere. So can you tell us a bit about your views on the possibility that Mars seeded Earth with this kind of life and how that may have happened?
Well, it's certainly the case that early history of Mars may have been more pleasant than the early history of the Earth. in fact, the moon forming event that created our moon would have been rather destructive on the Earth. Mars did not have such a cataclysmic moon forming event. So it may be, and people have speculated, that Mars was a better incubator for life than the Earth. And then the meteorites could have exchanged life. Now that's just pure speculation. We have no hard evidence that that's how life got started on Earth. But it's an interesting question, isn't it? And it gets to the heart of the matter of comparing Earth and Mars. So when we go to Mars, we don't just want to find life. We want to find life and compare it to life on Earth. Are they related? Did they share a common origin on Mars or on Earth? Or are they completely independent, separate? Is life on Mars a second genesis, a separate second genesis? Obviously, my preference would be for it to be a separate second genesis. That would be the most interesting case scientifically, but we have to let the data decide. Nature doesn't always take our preferences into account.
Well, and as you mentioned, that really brings us to my next question. Life on Mars is either an ancestor of ours or it's an entirely different kind of life, that second genesis you spoke of. How will scientists look for the differences and determine these two possibilities?
Well, this is a really good question. And the best way to answer it, I think, is by example. And really, we won't know the answer till we actually have to do it. It's one of those questions where you're not going to know how you're going to solve this problem until you're faced with the facts that you have to deal with. But we can do two very interesting what-if cases. One case is we go to Mars, we find evidence of life. It looks very similar to Earth life. It looks like it's our cousins. How can we confirm it? Well, the answer is we look at its DNA. If it's us, if it's our cousin that's got DNA, we sequence its DNA and we compare it to the DNA of Earth life. So that is the extreme what if. It looks like us. It turns out to be us. It's our cousins. Life is exchanged between Earth and Mars. It's another branch of our tree of life. We confirm it by DNA. Let's take another what if. We go to search for life on Mars and we find, and it really looks different. And it has some fundamental difference in its biochemistry compared to Earth life. For example, Earth life uses only left-handed amino acids in making proteins. Suppose we go find life on Mars and we find amino acids, but they're all right-handed. That is a fundamental difference that completely excludes it from being related to us, right? And so right away we know that it's a second genesis. So the broadest answer to your question is we will use biochemistry to tell the difference. And here are two examples. DNA could confirm a familial relationship with Earth, and asymmetry in the amino acids could confirm a completely separate genesis. And of course, there's lots of variations in between those two extreme cases.
So how would second genesis be more profound than if it turns out that we all come from the same family tree as Martian life? It turns out we're related, but what does it mean if we find another form of life out there, especially on Mars, something that's so close to us?
Well, for me, it's the big question of life in the universe. That you could apply here the well-known rule called the 0-1 infinity rule applied to life. That life in the universe could be 0, it could be 1, or it could be very, very, very many, essentially infinity. Well, we know it's not 0. Good news for that. We know that it's at least 1. So 1 is where we are. We're at 1. If we find a second genesis on Mars, we've gone to 2. But that is profound. The jump from 1 to 2 is really the jump from 1 to infinity. Mm-hmm. And so if we find evidence of a second genesis, that tells us that there are billions and billions of different types of life forms all throughout the universe. If right here in our solar system, it started twice, we know that life is independently starting many, many, many different locations. So going from 1 to 2 is a big jump in our understanding. And that's the question, the scientific question that motivates me. Can we get to 2?
Is it possible? And maybe we might see it more in Enceladus, and what would Titan's life look like? There's really so many different ways.
Right, 3 is even better, and 4 would be better, but the big jump is from 1 to 2. That's the big. Once you go from 1 to 2, 3, 4, 5. Okay, those are interesting, maybe worth a publication, but they're not the fundamental barrier that going from 1 to 2 is.
which makes it so interesting. And I know that NASA's Mars Curiosity rover and some of the other projects from NASA that are circling or on the planet Mars have really been kind of looking for these signs of life. There's possibilities that it's out there, and I know that some of the biggest discoveries have really kind of helped you probably with your work. So, what are these discoveries from these projects so far that have helped you get closer and closer to saying we think life is out there?
Well, on Mars, the recent data confirms again liquid water environment. To me, the most remarkable result of the Curiosity mission is the fact that at the bottom of Gale Crater, we found mudstones. So we landed in what we thought was a lake, and at the bottom of that lake, this crater, Gale Crater, was actually deposits that had been mud in a lake, mudstones. Most of the rocks we'd seen on Mars in all previous missions were volcanic rocks, basaltic rocks, which have zero interest to astrobiology. They're volcanic rocks, after all. Here, we were finding sedimentary rocks, not just sedimentary rocks, but mudstones formed at the bottom of a lake. It doesn't get any better than that in terms of searching for evidence of life. However, when we drilled down a few inches into those mudstones, we didn't find anything. There appears to be some sort of destruction mechanism on the surface, so we need to go deeper. But the fact that there exist mudstones on Mars that were deposited in the bottom of lakes billions of years ago is, to me, a fundamentally new insight, confirmed now on the ground. And so we can target those locations. We can say, we don't want to go land next to volcanic rocks. We want to land on mudstones and drill down and search for evidence of life in a lake that deposited those mudstones. And Curiosity's work at Gale Crater shows that that's possible.
Excellent. And these missions are really are looking for those kind of things. But what is it that we might be looking for that maybe will engage the general public a little bit more and say, we need to go to Mars. We need to make sure that we prove this. Is there any projects that are out there that you feel might get your average person to be excited about us going to Mars finally? I mean, the public's a little bit galvanized right now with TV shows and the movies and such, but what is it that somebody like you might be able to present to us in the near future that would get people out of their seats and say, this is a priority, we need to go see if there's life there?
Well, I would say two things might spark a big upsurge in interest in Mars. First is the discovery of organic rich materials below the surface. We haven't found organic rich materials anywhere on Mars. We've now found organics on Mars, but at very low levels. Such low levels that if those soils were on Earth, we would think that they were not very useful biologically. That may happen on a near-term mission with a drill, where we drill down a couple meters and we find something that's literally dripping with organics. Black dirt like you would see on Earth with many percent organics. That would be very interesting. It would, I think, raise the bar for biological interest. The other thing that I think would be interesting, both for biology and for human exploration, would be the discovery of large deposits of ice or even liquid water in equatorial regions. Mm-hmm. So the prospect that humans could go and use that water, either as ice or as water directly, liquid water, I think. And that there's interest now at NASA in mapping out the prospects for ice and water near the equatorial regions, because we realize that Mars has ice in the polar regions, but we also know that that's not where humans are going to go. Humans aren't going to set up a base in the polar regions. It's too cold. It's just too logistically difficult to get to. The human base is going to be near the equator. And so the question becomes not where is the ice on Mars and where is the water, but is there water and ice near the equatorial regions where we're going to have our base? So that question is finally settled in, and there's now a serious effort to try to map out the ice and the water in the equatorial region. And that, if we find a big deposit, I think that's going to be very exciting. People are going to say, well, we could land right there and we'll have water, we'll have ice. That's big for supporting a human base.
And that brings up a great point. So far, Mars is completely inhabited by robots. But, the work that they're doing are leading us towards human exploration in the near future, the next few decades. Musk wants to go. He wants to start a whole colony out there, as well as, what NASA's working towards with the journey to Mars. So what is it that a scientist astronaut would be able to look for that is beyond the current robotic capabilities that might, really say, hey, this is it? What is the scientist going to be able to do that connects us finally with saying we have found life on Mars?
Every study and every scientist that's looked at that question, what can astronauts do to advance science on Mars, in terms of the search for life, has come to the same answer: drill deeply. Robots are very bad at drilling so far, and humans are very good at drilling, mostly because they have hands. And so I think if astronauts were on Mars and they were calling me up and saying, what would you like us to be doing for science, astrobiology science, I'd say drill, 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 drill. Now, there's a lot of other reasons to send humans to Mars besides the search for life. Just to answer the question, can humans live on Mars? Is 1/3 gravity acceptable and so on? But within this restricted scope of astrobiology science, the answer to your question is drill deeply.
It reminds me of the movie Armageddon, where they had to send the oil drillers out to space. It was kind of one of the things that said, hey, this is what we're going to need to do. And it really does, it makes sense whenever we're looking for things, especially, that's what a paleontologist is going to look for. What are you going to do? You're going to dig deeply. That's how you're going to find the past life. And if we're talking about something billions of years ago, or even something that could be current, it's probably going to be that. Makes perfect sense.
Right.
And
go underground. Mars underground is the way to advance the search for life. And that's what I would want the humans to do, drill.
And people have also mentioned when you're speaking of underground, is that would probably be the best place for humans to be, is to maybe build a structure underground. Would those kind of fight with each other? In the discuss, and we're looking for life, but we also need to find a way that we can survive. Or should we really kind of stay more on the surface and then leave the drilling for the searches for life?
I think that question is still open. But my inclination is to go with your latter suggestion, to keep the base on the surface. And I would worry about being underground, worry about dangers, who knows what, and second, contamination. On the surface, any contamination by humans is cleaned up by the ultraviolet light. Whereas if you have the human base below ground, there is no cleansing effect of the surface radiation. So there's a lot of good reasons for staying on the surface. Now, maybe there's also good reasons for being in a cave or underground. I think that still needs to be worked out. I think it's too early to say for sure that we should go underground.
And what measures would an astronaut need to take to make sure that he is not contaminating things? How do we make sure that the life we bring with us isn't, something that ends up maybe tainting the research that these astronauts would do?
Yeah, that's it. That's a good point. And I think we have to accept the fact that when humans go, they will bring microbes with them. Our robots also carry microbes. We don't have sterile machines. We don't have sterile people. The secret is to not. The answer is not to prevent all contamination, but to make the contamination minimal and reversible. And I think the answer that there are ways to do that. And the surface of Mars, in some sense, works with us in that, because the strong ultraviolet radiation on the surface of Mars kills bacteria from Earth. So anything we release on the surface will be cleaned by the environment. And that's one reason why I worry about setting up the base below the surface. Mm-hmm. Then you've removed yourself from that cleaning environment, and you're more likely to contaminate the environment and to compromise the basic science that we went to Mars to do.
And this kind of brings me to my next point, is that we're discussing looking for life, but there's also the talk of settling on Mars. Elon Musk has talked about it. In the next 10 to 15 years, he wants to start sending people. It's a big dream, and it's a dream that a lot of people are paying attention to, because he's doing it on such a public stage and he's had so much success. But that brings up the topic of terraforming. How are we going to terraform the planet? There's different ideas out there. The Mars Terraformer Transfer is a plan to heat up the planet by striking it with an asteroid. Musk himself has discussed nuking the planet, which he further clarified as saying that he wants to have tiny pulsing suns over the poles. But in your expert opinion, are either of these ideas the right way to go about terraforming, or is there a more obvious process that maybe we might be missing?
Well, there is an obvious answer to how do we warm up a planet? And the obvious answer is we're doing it on Earth.
Yeah,
That technology is uh, not only been developed, it's been deployed. We are doing it. We are in denial that we're doing it. We're definitely doing it.
indeed.
And that technology, greenhouse gases, is the simplest, most direct way to warm up Mars as well. It may be possible to warm up Mars with nuclear weapons or asteroid impacts or giant mirrors in space, but we have no experience with any of those. We don't know how they work. We don't know if they work. We don't know anything about them. What we know is greenhouse warming. So why not use it? And it turns out to be quite simple. So I don't see any need to invent a new process. We have one that's working. We're testing it out right here on Earth. And it's exactly what we need for Mars. Global warming. On Earth, it may not be a good idea. Depends on where you live. If you live in Florida, it's a bad idea. If you live up in northern Canada, it's a wonderful idea. But on Mars, global warming will be a good idea everywhere.
And we're really doing that through the process of billions of people expelling through their vehicles and industry and everything else to do so. What is a way that we could utilize this there when there's nothing and no one there?
Right. On Earth, we're doing global warming without even trying.
Mm-hmm.
We never really came up with a plan that said, let's warm up the Earth and here's how we're going to do it. It just became accidental. Producing CO2 and also producing greenhouse gases like chlorofluorocarbons and perfluorocarbons. On Mars, we could be more clever, systematic, and more effective. We could choose the gases we want to produce them on Mars using in situ resources, release them into the atmosphere, and then allow that warming to release carbon dioxide from the polar caps and set up a cycle. And we did a study of this a few years ago and published a paper, and we analyzed the various choices for gases, and there's some clear winners. The winners are simple carbon, fluorine, sulfur gases. We wouldn't want to use bromine and chlorine because they destroy ozone and other compounds which have a short lifetime. So if you go through all the requirements, the gases that one wants to use are SF6, CF4, C2F6, and C3F8. This combination of gases makes a very effective mixture. We could produce it on Mars from the carbon, sulfur, and fluorine in the environment. We don't carry it from Earth, and release it in the environment, and it will warm up Mars. And as it warms up, carbon dioxide and water will come out of the polar caps. The atmosphere will get thicker, and there'll be a feedback process. And that's really the effective way to warm up Mars.
And we've seen from the evidence that Mars' atmosphere has been stripped from the planet. What are the ideas surrounding that? What actually happened to it to begin with? And maybe something I think I've heard the idea that it might have had a core, like a moving core that possibly stopped. What is it what is the most recent research saying about what happened to Mars' atmosphere to begin with billions of years ago?
Yeah, the idea is pretty clear that billions of years ago, as you say, Mars had a thick atmosphere and it lost it. Mm-hmm. And so the question that raises is, if we terraform Mars, won't it also lose that atmosphere? And the answer is yes, it will. We're not going to make Mars larger or start plate tectonics or start the core spinning, creating a magnetic field again. But the point here is an important one, that billions of years ago, Mars lost its atmosphere over a time scale of about 100 million years. Well, looking back billions of years, 100 million years is a short time. So we say Mars lost its atmosphere rapidly. Well, rapidly back then was 100 million years. Looking in the future, if Mars loses its atmosphere again rapidly, 100 million years, well, 100 million years isn't rapid at all. It's a long time in the future. So probably if we make Mars habitable, it won't stay habitable forever. It might only stay habitable for 100 million years or so. Well, that's okay. I'm okay with habitable for 100 million years. And after 100 million years, somebody else can pick up the problem.
Well, and I guess I would ask, but is there any possibility for an answer to that question? If we were able to create an Earthling-friendly atmosphere on the red planet, could we keep it? Would there be a way to keep it? I mean, if you're saying beyond, if it's going to last for 100 million years, I guess we're going to be okay. But would there be able to wait? Is there a current way that we think we could sustain it indefinitely?
Well, if you're talking indefinite, I wouldn't start at Mars. I'd start on Earth.
Mm-hmm.
Earth is not going to live indefinitely. Mm-hmm. Our current theory suggests that Earth will become uninhabitable in about 500 million years due to the brightening of the sun. It'll become Venus-like. So if you're taking a long-term view and you want to find a home for hundreds of millions of years or billions of years, don't worry about Mars, worry about Earth, because that's going to go bad. And then eventually, of course, in 5 billion years, the sun goes red giant, and then both Earth and Mars are toast. So once you start thinking beyond the 100 million year time frame, there's a lot of problems. Mars is not the biggest one, Earth and the sun. So I'm only thinking 100 million years. I'm not extending the window beyond that.
Let's hope we make it another 100 years. Is kind of where I'm sitting.
Yeah, exactly. So 1,000 would be really great. 1 million would be wonderful. 100 million, okay, that's way beyond the horizon.
And what will we have evolved into in 100 million years? That's a whole different conversation. But who knows? So thank you so much for the conversation today. Where can people find out a little bit more information about your work? And is there anywhere they can follow you on social media?
I'm not on social media, but NASA does have a website. They have a page for me that lists my publications and papers that they can read if they're interested. Mostly what I write are scientific papers. Occasionally, some articles for more public magazines like Astronomy or Scientific American. But they're all listed on that page, and people can find them then on the internet.
Excellent. Well, thank you so much for your time today, and we can't wait to see more of your research and see what you do next, and we appreciate your time.
Good talking to you.
All right. Thank you so much, guys, and we'll see you on the next episode.